All right, so picking up because my microphone died. Sorry you missed the first couple seconds of this if you weren't here. So our last one, arcsecant, like I was about to say, this one doesn't really show up in the wild just because of the format of it. Because what's down here in the bottom? Absolute value of x, yeah. That one, it kind of makes this one hard to blend in with something that looks like it might be something else, which is kind of what happens with a lot of these. They look very similar, but there's different techniques to do with them. So we have the absolute value of x, and then from there, we don't have 1 minus x squared like sine. We have x squared minus 1. Yeah. Right. So those are our three inverse trigs, and of the three, the two that we're really going to focus on today are arcsine and arctangent. So the first, we're actually not going to complete the square with these first two. These are two integrals that we could solve with u substitution. These will help you kind of look for patterns that can help you see that you might have something that's going to work with arcsine or arctangent. As a matter of fact, anytime you see a square root like this in your denominator, that really should throw you like, hey, I should definitely consider arcsine. Is that going to help me out here? But there's a problem with this. This isn't just arcsine. What's wrong with it? The 4 is what's wrong with it, okay? So what has to happen is, in order to find an antiderivative for this, you have to have a 1 here. You have to have a 1, can't have any other number. This, the x squared, is what's allowed to change because we can use u substitution to get that to be u squared. Instead of like x over something or some weird multiple of it. So what we're going to do is we're just going to factor out a 4 from this expression underneath the square root bar, which is going to give us our 1 minus, and then we'll have to use u substitution to fix what the problem that makes with the x. So let me show you what that means. This is equivalent to the integral of 1 over square root of 4 times the quantity 1 minus, yeah, 1/4 x squared, or I'm just going to put x squared over 4, but you're right. I mean, the two things we're saying are equivalent. Okay. So I have written algebraically an integral that is equivalent to the integral that I had to start with. So I can always do that. I'm going to pull 4 out of the square root bar. What does 4 come out of the square root bar as? 2. Yep. Cool. So now I have the integral of basically 1/2, right? So, you know, if you see a coefficient completely being multiplied, you're thinking of this, we may not need this. This might just be a coefficient, so I can bring it out. It is going to turn out, when we do the u substitution, that 2 is actually just going to disappear. We'll see why. But I have the square root of 1 minus something squared, right? And that's what I need in order to have arcsine. So I'm going to identify this something squared as u squared. Okay, we did that once with u substitution, so we're just seeing it again. So in this case, I say that u squared is x squared over 4. But I want to know what u is, so I square root both sides to get x over 2. And that makes du equal to what? What's the derivative of x? 1/2. So du is 1/2, and what else do I have to write? Dx. Yep. Cool. Which, and normally at this step I say, but we don't have 1/2 dx. But we do have 1/2 dx, don't we? Like, yeah, we have exactly what we need there. So du shows up right in here. This is the integral of 1 over the square root of 1 minus u squared du. So I replace the 1/2 in the dx with du, and I replace the x squared over 4 with the u squared, and that is, by definition, the arcsine, or the inverse sine of u. So when you do this technique where you know you have you're trying to match to this antiderivative, you are trying to figure out what, normally we're trying to say like, hey, what's our u? But with this method, I say, well, I want this. I want to know what's taking this guy's place. So I say that this x squared over 4 is taking the place of u squared. And it really is. It's because I have a u squared in my antiderivative. That's really the reason why, and it's specific to this technique. It's specific to to inverse sine ones. So I have the inverse sine of u plus c, which is the inverse sine of x over 2 plus c. There is a way where you could teach this where like you kind of figure out what u is. You're like, oh, okay, so like I could have started there, but I just like to identify it that way. Like, okay, if this is my u squared, what's my u? But I just feel like it's easier as long as you know you're working with this stuff. First, identify your u squared, write it out to get your u. You end up doing the same thing both ways. Don't miss this part, the fact that, you know, it's u that you're plugging back in here. You know what I mean? It's the sine of inverse sine of u. So it is the inverse sine of x over 2, not x squared over 4. Questions on that one? The second one's an interesting one. I always like this one. When you're looking at this, and again, there's going to be a point where we're going to know 6 or 7 different techniques. We're up to 3 now with our u sub and our long division. And you kind of have to say, what do I do with this? I always say the first step is u sub. So if you say that u is x to the 4th, what would you be looking for in your numerator? X cubed. Do I have x cubed in my numerator? No, so that's not it. But if you say, hey, maybe this matches up with arctan, now this wouldn't be our u, this would be our u squared. If this is u squared, what's u? If u squared, x squared, and if I've got u to x squared, what's du? 2x, right? Which is what I have. I have an x, and I can put the 2 there. We can deal with coefficients. So here's an example of one where we'll say that our u squared is x to the 4th. And to some degree, this is a little bit of like puzzle solving. Like you're trying to break the puzzle of like what happened to get us to here when we took the derivative. And this is what happened. So that makes u equal to x squared, du equal to 2x dx. But we don't have 2x dx, we just have 1x dx. So we'll say 1/2 du is dx. Boom. Yes, thank you. Yep, I like killed the x with the 2 as well. All right, so it looks like I have this is equal to 1/2 x dx is my 1/2 du. And x to the 4th is u squared. So my integral is just 1/2 of arctan. Plus c, which is 1/2 of arctan of x squared. Plus c, of course. The other thing I'll say here is this one especially, imagine this process going in reverse. You would do the chain rule, which would mean you'd take the derivative of the inner function. That's where you would get your 2x times 1/2. That's where your x comes from, right? And then you would just be plugging that x squared into 1 over x squared plus 1. So you'd have x squared squared. That's where the x to the 4th comes from. Cool. All righty. Everybody's favorite, completing the square. This is the real portion of this lesson. Like this is what we need to know how to do. Make an equivalent expression to the one below by completing the square. We're not solving a quadratic with this method. We are doing something else. May you remember how to do this? Okay, yeah. Did you watch it with the? I like these. So I'm going to try and it's called completing the square because we are going to make a physical square out of these algebra tiles. So we have x squared. So this is a square. The sides represent x, some quantity that we don't know. These guys represent x's. These are x by 1. So we have x squared plus 4x. Sorry if you're watching this video. You have no, it's between the phone call and what I'm now doing on the board, which you guys can't see because it's physical. But And we're going to put those 4x's. And the key to completing the square is you've got to break these two things up evenly, right? So I have x squared plus 4x. These are supposed to be 1 by x. Completing the square is filling in little 1 by 1 units in here to figure out what gives me a square. So that's how we complete the square physically, looking at it. How do we do it on paper when we don't have little fun rectangles to play with? What you do is you write out your x squared, your 4x term, because those are the things that kind of lock this in place, and leave some room for 7. That's funny. I was talking, that was Brogan on the phone, and I'm going to steal one of his words. And you may remember from years and years ago, Mr. Brogan saying, adding a fancy form of 0. My students remembered that last year. No? Maybe, I don't know. You guys were half and half. Was that the COVID start? That was the COVID start. Okay, right. So yeah. Well, that's one of Brogan's lines. So, oh, good. So what we're going to do is we're going to add the 4 to complete the square and then take it right away. Yeah. So all I did there, and the idea, what we're doing when we're completing the square is we've got to figure out what number we're going to do, but we're just going to add it and then subtract it away. Adding a fancy form of 0, which adding 0 doesn't do anything. So what I end up with is I can take these first 3 terms and factor them, and they will factor into a perfect square. That's what we mean when we have a perfect square. If I did a picture like that, I get a square. And this factors into x plus 2 squared. And I was supposed to change that from a 7 to a 5 so it matches the problem below. So I'm going to go ahead and just pretend that this problem always said 5 and that I made a mistake when I wrote 7 there and fix the mistake that I made so that it says 5 because the math just works out easier. And then negative 4 plus 5 is 1. Yep. So the original expression with the 5 where the 7 is equivalent to the expression that I have down here. Because this is x squared plus 4x plus 4. This was x squared plus 4x plus 5, so I was 1 short. That makes it 5. Okay. So there's one example, and then we're going to use that. We're just going to basically, when we get down to our integral down here, u is x plus 2. And then all of a sudden we've got u squared plus 1. But let's take a look at what's going down. These sine ones are a pain in the neck. Because in order for sine to work out, the x squared is negative, which means you're going to see that anytime you have one of these, that you've got a negative in front of your x squared. That's kind of goes hand in hand. If you have a positive x squared, this integral gets solved a different way, and it's not a way that we learn in AB or BC Calc. So let's take a look at it. What we have to do with this one is we actually have to first factor the negative out so that we end up with a positive x squared. So I'm going to factor that negative out, and I'm going to write the terms in the correct order. So I'll write negative the quantity x squared minus 8x minus 9. And now I'm going to complete that square inside of those parentheses. And in my very last step, I actually have to pull this last piece out of the parentheses. So there's a couple extra pieces to this one here. This is where some of the formulas come along. Now, obviously, I did it just kind of, I just did it by drawing it. But if I had 4x, how did I know that I was going to take those 4 and put 2 here and 2 here? Easier than that. If it was 6x, how many would go on each side? 3 and 3, right? And then, of course, I would need more yellows here. If it was x squared plus 8x, I'd put 4 and 4. The key is you're making a square, so you're not splitting them up unevenly. You know what I mean? You're not going to get a square if you put 5 of them here and 1 of them there. You've got to split them up evenly. So you just divide that b term by 2. Okay, so that's how I knew to put that's how I knew to put 4 here. This quantity represents b over 2, which is how many of the b green rectangles you're going to put on the bottom and on the side. And then the number that you add at the end is that squared, because where does that come from? It comes from here, b over 2 squared. Okay, so that's what I have to do here. Negative x squared minus 8x. Bring my minus 9 out back here. B is 8, negative 8. B over 2 would be negative 4. And negative 4 squared is 16. So I'm going to, I'll even do a different color on this one. So I'm going to add my fancy form of 0, add 16 and subtract 16. That has not changed anything. And here's where I've got to be careful. I've got negative the quantity. Whatever, we've already figured this out. So this is always going to be something squared. What did we square to get 16? Negative 4. That's going to make this x minus 4 squared. That takes care of the first 3 terms. And now I've got negative 16 minus 9 at the end, which is negative 25. Don't be surprised when you see perfect squares come out at the end. Like when you get a perfect square there, that makes you feel like you did the right thing. Because in the end, we're going to need to know what the square root of that number is. So anyway, last but not least, we want to get rid of that big parenthesis out of the outside, because in the end, we're trying to match arcsine. And arcsine is 1 or a number minus x squared. So I'm just going to distribute the negative in. So now I have negative x minus 4 squared. And negative times negative 25 is plus 25. So although it's in backwards order, that's equivalent to having 25 minus x minus 4 squared, which is at least close enough to the form of 1 minus something squared. We'll have to divide everything by 25. All right. So now let's solve some integrals by completing the square. 1 over x squared plus 4x plus 5. We know from above, because this is the same one as before, that this is equivalent to 1 over x plus 2 squared plus 1. And then dx. Because we completed the square above. That could be u sub. That could also be linear u sub, right? U is x plus 2. Du is dx. This is going to work just like 1 over x squared plus 1. But the argument isn't x, it's x plus 2. Okay. Should I do the u sub just to, I don't know. I'm going to do it. But we're going to find out that we're just going to get arctan of x plus 2. So let's do it to make sure we see all the bits, all the moving pieces here. We'll make our u equal to x plus 2. Or I could have said that my u squared was x plus 2 squared. I feel like in this example, it's a little bit easier to go right to u. Maybe not. So our du is 1 dx, yep. Yep, just 1, but du equals dx. So basically, we have the integral of 1 over u squared plus 1 du, which is identically arctan. Cool. So yeah. Yep. So yeah, so definitely possible to do that without actually writing out all the u sub by just spotting it. But there's also nothing wrong with doing the u sub, so you know you're doing the right thing. Alrighty. Likewise, in the second example, we know that this is the integral of 1 over the square root of negative x minus 4 squared. So let's bring that to the end so that it matches our arcsine a little bit better. And then a positive 25, so 25 minus Now that's a problem. I can't go right to u sub with this one because in order to work with the arc sign, I need to have this be a 1. So I'm going to factor a 25 out of this expression. This will be really similar to what we did earlier. So that's the square root of 25 times the quantity 1 minus x minus 4 over 25. And the x minus 4 is squared. Bring the 25 out of your square root as a 5. That's why I said you shouldn't be surprised when you see a perfect square in there. It still works if that's not a perfect square. You just have an ugly number in your problem. And then this is a feature of, we saw this up above in our earlier example. This is a feature of the arc sign. We're going to make our u squared equal to x minus 4 squared over 25. So let's do that. U squared equals x minus 4 squared over 25, which makes our u equal to x minus 4 over 5. And that makes our du equal to, 1/5 dx. And just like above, like I said, this is a feature of arcsine. It's just the way it's going to generally work out. Usually I say, but we don't have 1/5 dx. And the only reason we don't have 1/5 dx is I forgot to write my dx's. So we do have 1/5 dx. So that we are going to be able to just, as is, plug in with du. So we have the integral of 1 over 1, the square root of 1 minus u squared du, which is arcsine of u plus c, which is the arcsine of u, which is x minus 4 over 5, plus c. Fun stuff, right? Got about a handful more examples here. Just a -4 thrown up at the top for the heck of it. This time we have 4x squared plus 12x plus 13. So now I have 4 blocks of x squared. I've got to use all 12 of my greens. How many greens? Well, start here. How many greens are going to go below if I've got 12 greens, and how many are going to go to the side? 6. And then how many are going to go in each column? 3, right? So I had to divide by 2 here twice to realize that, the sort of, the 3 is my number, right? I got to go 3, 3, 3, and 3. So how many yellows do I need? 9 of them, yep. Just 9. Yep. Hey. I think all of the papers are on your desk, Kaya. Except for the review, which I was... yeah, there were 2 of them. Or there's only 1, that's right. So I have 12 greens to work with, right? 4x squared plus 12x. And I've got to make, this thing has to be a square, right? So the dimensions going down the left have to match the dimensions going down the right, and everything needs to get filled in. And there we go. So where does that come from? How do I figure out that it's 9 with the 4 and the 12 there? So we do have to take our b and divide it, but we have to divide it twice. We've got to divide it by 2 because half of our greens are going to go on the bottom and half of our greens are going to go on the side. But then we have to divide it by how many blue blocks we have in a row or a column, which is, in this case, since I had 4 blue blocks, the square root of 4 is 2 by 2. So you've got to divide by 2 over the square root of A.
Should those cards be fixed?
What do I have? I have 2A, don't I? Yep. They should be fixed. Good call. Yep. You know what I was thinking? I don't know what I was thinking. Yep. I had the quadratic formula in my head. And I was thinking that the B over 2A is from there. Alrighty. So that's going to be, in this case, 12 over 2 root 4, which is 12 over 2 times 2, which is 3. And then our B over 2 square root of A squared, which is what we're going to complete the square with, is going to be 9. So B over 2 square root of A represents the side length of one side of the yellow square. So the 3 by 3 square that I have here in yellow. So then squaring it tells me how many yellows I actually have. So now we'll do this all in place. We've got the integral of -4 over 4x squared plus 12x. Leave 2 spaces plus 13. And that's going to be dx. I'll just put it there on the top. And then like we figured out, the number to add and subtract is 9. So plus 9 minus 9. Which gives us the integral of -4 dx. Both your first number and your end number should be square rooted. So I'm going to get 2x plus 3 squared. And that matches what I have here, 2x plus 3, 2x plus 3. That 3 we already figured out, that was over here. That's just going to be the square root of A. And then -9 plus 13 is 4. Yep. Cool. All righty. But I don't want a 4 there. I want a 1. So I need to factor a 4 out. So I've got the integral -4 dx over 4 times the quantity. I've got to factor a 4 out of that. So that's 2x plus 3 over 4 plus 1. Because it's just multiplication and I didn't want to put it right up against this. Good question, but that's what happened. No good reason. Just a bad reason. But I think I was doing that when I was doing my work also, because just to remind you that it doesn't matter where it is. So it's good to keep seeing that so you kind of get that idea in your head. Alrighty, so that makes, now with my U substitution, just for organization here, change my color. U squared is 2x plus 3 squared over 4, which makes U equal to 2x plus 3 over 2, which makes du equal to 1. Yeah, dx. Yep. Yeah. Correct. All right. So that's not bad. I can cancel these 4s back in my problem. Du is dx. With the exception of the negative sign, I basically have arctangent. So the integral of -1 dx, or that could just say negative dx, weird looking dx, u squared plus 1. And an extra long fraction bar, which is negative arctangent of u plus c which is negative arctangent u was 2x plus 3 over 2. That's one of the things that definitely happens with these is you end up with weird arguments of your arctangent like that. Yeah. This is a perfect square trinomial which factors to 2x plus 3 squared. That's what we're doing. That's why we added 9 and subtracted 9, and we figured that out with these formulas. This is a hard example. We did a much simpler example earlier, so you're just seeing the hard example first, but that's the idea. This is completing the square. You heard about it once before, Algebra 2 probably, before you did the quadratic formula, but that's what that piece is. And then last but not least, believe it or not, this example, at least for example 5, isn't going to take super, super long because when we go to complete the square here, this one, I don't have a coefficient in front of x squared, so that is going to make it easier. So when I go to complete the square, I get 1 over x squared plus 4x. I don't have to put, there's no constant, so I don't have to put anything back here. I'm going to cut this in half and then square it to figure out what my fancy form of 0 is. Half of 4 is 2. 2 squared is 4. So I write plus 4 minus 4. So that is the integral from 1 over x plus 2 squared. So that thing that you square is what your number is inside of your factoring. Dx, dx. Can I make arctan out of that? I could divide this whole thing by negative 4, right? That would get me the positive 1 that I want here. But this would be negative x plus 2 squared over 4, which would be my u squared. And that would be a problem when I went to take its square root, because there's a negative there. We do not know how to solve this yet. So the signs absolutely matter. In both arcsine and arctangent, the number that you have left over after you complete the square has got to be positive. And if it's not positive, you don't know how to solve it. Okay? There is one problem in the last section, the last non-AP section, where that's going to happen. It says one of these you won't be able to do. So there's only one to look for in the problems. All right. Let's do one of these, and then I want to make sure I give you guys some time to work on them. I want to look at this one. E to the x over 1 plus e to the 2x. First thing we should do is check u sub, right? If I was going to use u sub, what would be a good candidate for my u? E to the 2x is possible. But du would be 2e to the 2x. Do I have e to the 2x there? I mean, outside of this, because this would get, that's not e to the 2x. No. But keep in mind that e to the 2x is another way of writing e to the x squared. So could I make u squared equal e to the 2x? Because then u is just e to the x, and du is e to the x dx, which is exactly what I have. So we end up with the integral of e to the x dx is just du. So let's throw du in my numerator. And then 1 plus e to the 2x becomes 1 plus u squared. So we have inverse tangent. Which is tan inverse of e to the x. Yep. A function that only exists for calculus class. Has no real good purpose to exist otherwise, but that is what it is. All right. What we'll do is we'll take a look at these other two examples. This one, I'll point out, you need to do long division. And when you do that long division, because you'll see, I think you'll see one like this in the homework. When you do long division, you're going to get, it's actually really easy to see because you're only going to be able to divide once because you're dividing x squared by x squared. It's basically just going to come out to where the remainder is plus 1 over this. And then that remainder is just a simple-ish completing the square problem. So that one, it would take a little bit of time, but I'd rather give you guys some time to practice. This is one I'll go over at some other point. I don't believe there's one like this in your homework. This is one where you would start out with some u sub, but you don't get exactly what you're looking for. As a matter of fact, I think I may have wanted to change what number is right here anyway. No, I did. No, I made the change. Never mind. I did make the change. No, so this one is good. You don't get exactly what you're looking for here, so you almost do another fancy form of one sort of thing. But this one I'll definitely do, and this one will, in some way, shape, or form, take a look at. But yeah, I want to give you guys some time to at least try to complete some squares.